What's up, guys? This is Matthew Burns, and in this tutorial, the second tutorial in a series on how to make a persistence emission display, we are going to go over the electronics and the circuitry that I designed to make this work. In the following tutorial, we are going to go over the programming of the microcontroller that I'm using, the PIC16F870. And in the tutorial after that, we're going to put it all together with the mechanical stuff, mounting it and testing it out. So, for this tutorial, first, this entire persistence emission display is based around the PIC16F870, not because it's optimal for this. I am trying to control 16 tricolor LEDs, common anodes, so 48 LEDs, with two 8-bit ports. Not really the best thing, but I'm able to make it work, so that's fine. One downside, though, to using an 8-bit microcontroller is that when I have 96, I believe, unused general-purpose file registers in Bank 0 on this microcontroller to store certain columns of this of the persistence emission display in, I have to divide that by 3 because it's red, green, blue, so then I have 32 columns. I can make 16 by 32. But then because each one of those can only hold 8 bits, and this is a 16 pixel high device, I have to divide that by 2 again. So the image will only be 16 by 16, but as long as it works, I'll be happy. So the only two ports that are complete on this microcontroller are port B and port C. And they are 8-bit ports to 8-bit microcontroller, so we are going to use those two ports to send power to the LEDs. The first LED, the top LED, is going to be connected to RC0, and they will sequentially go down. The first LED is RC0, second RC1, RC2, RC3, RC4, RC5, RC6, RC7. And then the last 8 LEDs will be connected, the 9th one to RB0 and the 16th one to RB7. So I'll use port C and port B. A note on port B. I was having trouble getting pin 24, RB3, the 5th from the bottom LED to light up, and I couldn't figure out why that was. I thought at first that I'd burnt out an LED. It's actually not. This pin is also involved in some low voltage programming, something or other that I haven't done anything with. But either in your code or in the configuration bits, which we'll go over more next time when we go into programming, you want to turn off the low voltage programming because we're just going to use it as a common standard input-output, in this case output. The other pins we're going to be using are, well, obviously, we're going to need to hook the microcontroller up to power, VDD, and ground, VSS. Both VSSs have to be hooked up. MCLR, actually, I'll go through that later because I have a special note on that. 3 pins we're using to control the grounds from the LEDs because I have all the grounds of the red connected, all the grounds of the green connected, and all the grounds of the blue connected. If that's not clear what I'm saying, I'm going to draw it out here. So, these are tricolored LEDs, so I'm going to draw 3 LEDs for one. I don't really know the symbol for a tricolored LED, and frankly I don't care too much because it's not important. If I can make this work, that's the only important thing. So I have one tricolored LED there. I'll draw 2 because I don't feel like drawing all 16, and I don't know if anybody wants to sit through that. And if you don't know what I mean by common anode, here's where I can show you. So here's the anode of all of them, here's the cathode of all of them. All of the anodes are connected. So they have one common power. And then 3 separate grounds. So let's say this is the red LED, this is the green LED, and this is the blue LED, and we'll say the same for the top. This is the red LED up here, this is the green LED in the middle, and this is the blue LED on the bottom. We're connecting the ground of the reds together, the ground of the greens together, and the ground of the blues together. Someone commented on me about wire connection. In case anybody is unfamiliar, which most of you should be, but when creating schematics on the computer became more popular, like EagleCAD and stuff like that. It might have happened before that, I don't know. But software like that, drawing this loop to show that the wires are disconnected became less and less important. Now to show that they're disconnected, you draw over. If you wanted to connect them, you'd put a little dot in the intersection. It makes no difference how you want to do that. The point is, as you can see here, I have the ground of the reds connected, the ground of the greens connected, the ground of the blues connected, and then I'll have each of these go to the... It's not really good the way I drew it, they're kind of clustered. Go to the collector of a transistor. This transistor here we're using is the TIP 31 transistor. The emitter of the transistor is going to go to ground. So we can connect and disconnect a certain color of LED from ground. And then the base, it'll be controlled by the microcontroller. So we'll have 3 of these transistors. I don't know what I just drew right there. 3 of these transistors. Sorry, this is really messy, I know. And they all go to ground. The red connects to port A0 on the microcontroller. The green connects to port A2 on the microcontroller. Or port A1. The blue connects to port A2. So that's how we control which color of the LEDs we're controlling, because we can't control 48 LEDs at the same time with 16 input-output pins. What we are going to do is, because I don't want to have to deal with pulse width modulation or anything, we are going to, on one trip around this persistence of vision display, if I didn't make it clear last time, it's going to be spinning around extremely fast on an arm with the LEDs vertically mounted, and it's going to blink the LEDs at the proper time to draw an image in midair, stationary image. Because I don't want to deal with pulse width modulation, and the microcontroller we're using is kind of underpowered for the job as it is, I don't really want to get into that. So what I plan to do is I plan to turn on the red LEDs one time around, the next time around turn on the green LEDs, the next time around turn on the blue LEDs. This way I only have 16 LEDs to deal with at a time, and to control which color I'm using, to control which color is currently being controlled by port B and port C, I have these 3 TIP31 transistors. And so those go to port A0, port A1, and port A2. We're using one other pin on port A as an input this time to get input from the Hall effect sensor, which is that piece right there. More on that later. I'm going to explain how that works, as it's kind of important, although you could build it, I guess, without listening to that, but that'd be no fun. So if my camera will focus, which obviously it won't, because that's just the way it has to work. Thank you, camera. Really, I appreciate it. So, well, anyway, if you can see, it's not very clear, but if you can see anyway, there's a wire going from the Hall effect sensor to pin 7 on the microcontroller. That is port A5. And we're using that as an input. Now, another note on that, I was having trouble getting the microcontroller to read inputs, and I couldn't figure out why. I set it up as an input. I was testing to see if that register was high or low, but for some reason it wouldn't read the input at all. So I decided to try something. I decided I'd go to the ADCON, the analog to digital converter register, and set all of the set port A as all digital and nothing analog. And after I did that, it worked. So I'm not sure if right off the bat by default the inputs aren't working because they're expecting something analog, or what the deal is. But for some reason I have to set all port A inputs as digital. So if you have that problem, it's because they're probably expecting an analog input and you to do something else with it. But again, I can show you better what I mean tomorrow, or next video, when I actually go over the code. In addition to the circuit here that flash the LEDs, we also need to be able to program this thing in circuit, because no one's going to desolder and solder their PIC every time they want to change the image. So I'm programming my microcontroller with a Picket 3 from Microchip. And there are 6 pins here. We're only going to deal with 5 of them. We usually only ever have to deal with 5 of them. The first one is VPP. We're going to hook up to the first pin. That's also MCLR, where you're supposed to have that tied to power for the microcontroller to operate, and when you pull it to ground, it resets the microcontroller, just like if you were to shut off power and turn it back on. So we need to have the first pin connected to MCLR, and the problem with that is when you're programming, MCLR pin will experience about 13 volts or somewhere around there. The problem with that is that if you have MCLR strictly tied to power, which is also tied to VSS, or not VSS, VDD, which is power, you're going to probably end up destroying your microcontroller, as it's only meant for like 5 volts or something like that. So what I do here is I connect MCLR to power through this resistor and ground through this capacitor, nothing special. If you wanted to put a switch here in order to reset, you could, but it's not like you're going to put your hand on the circuit board and try and reset it while it's spinning around at 3000 RPM, so I wouldn't worry about the switch. But right here is the important part. I have a diode here isolating MCLR, or isolating power from the voltage that it'll be experiencing from the programming circuit. So this diode here isolates the programming circuit from the main circuit. So if MCLR is still tied to power, but the 13 volts will not leak into the rest of the circuit. That's a IN4001 is what I'm using. It's just a rectifier diode. Any rectifier diode will work fine. The second pin, the second slot on this right here, or whatever, right there, this wire here will be going to VDD, power on the microcontroller. The third one will be going to VSS. It has to be connected to both of them. The fourth one will be going to pin 28, which is data, and the fifth one will be going to pin 27, which will be the clock. So that the last 4 pins that I told you about don't need to be isolated in any way from the rest of the circuit. If you build it just like this and include this diode here, the rest of your circuit will not interfere with the programming and it'll work fine. The last thing I wanted to mention about this circuit, I will, by the way, post a complete schematic of this on the webpage at Electroburns, but the last thing that I wanted to mention in the video part of this tutorial is the Hall effect sensor. So the Hall effect sensor, obviously you can tell from its name, is based off the Hall effect, which works on, well, is actually based off the Lorentz force. So the Lorentz force states that if a charged particle is moving in and perpendicular to a magnetic field, though it doesn't have to be completely perpendicular, because obviously if it's not completely along, then a vector component of it will be perpendicular to, that charged particle that's moving in and perpendicular to the magnetic field will experience a force perpendicular to both the direction of its current and the magnetic field. So for example, I drew this square wire last time. This is the second time I tried to do this video. My battery ran out. But I am going to draw a square wire, not a circular wire, just because it's easier to see the different directions on a square wire. And I have current moving along the square wire in this direction. Based on what I told you, if the current's moving in this direction, and I apply a magnetic field across this plate, for example, I have a north pole of a magnet below, and a south pole of a magnet above, and I have a magnetic field moving up this way, then the particle is going to be pulled in this direction. Now, I'm not really sure which direction it would go. Well, actually, we'd have to think about this a different way. Most people are familiar with the right-hand rule, where, let me think about this, your fingers would go in the direction of the magnetic field, your thumb would go in the direction of the current, and your palm would be in the direction of the Lorentz force. Now, that's fine and all if we think in a very conventional way about electronics as a positive charge moving along a wire, but in reality, electrons are negatively charged, and they're moved from the south, what am I talking about? The negative terminal of the battery to the positive terminal. The reason why we can think of it as a positive charge moving from the positive terminal to the negative is that a negative charge moving in one direction is the same thing as a positive charge moving in another. If you think of a wire here, and you have some lattice of copper ions, whatever, a bunch of positive charges, and then you have electron here. As the electron moves to this positive charge and continues to move along, it might make that negative, but it'll free up a quote hole unquote there, positive charge. So it looks like the negative charge moved this way, but well, which it did, but it also looks like the positive charge moved this way. So you can think about it both ways. But what I'm trying to get at here is when you're thinking about electrons which are negatively charged, you'll actually have to use your left hand instead of your right hand for this rule. So we're not going to worry about which direction the charged particles are moving or anything like that. Just the only thing you need to get from this is that when a charged particle is moving in and perpendicular to a magnetic field, it will experience a force, known as the Lorentz force, which will pull it perpendicular to both the direction of the current and the magnetic field. So what that's saying is that the charged particles, the electrons, will build up on one side of this wire or plate or whatever it is that you're running current across, and they'll be depleted from the other side of the plate. Now, we can measure the potential. If we stick a probe on one side of the plate and stick a probe on the other side of the plate, we can measure the potential difference across those two plates, and then we can run those into some other circuitry and generate a digital signal based off that. That is exactly what this here does. This here has a plate in one end, and rather than having to pass a magnet by it, it has a magnet in the other tower. So one of these towers is a plate. I don't know which one's which, but one of these towers is a plate, and the other one of these towers is a magnet. And so the electrons passing through the plate are always experiencing the Lorentz force, and they're always across the plate, as we can measure the potential from one side of the plate to the other, is always experiencing a Lorentz force and always generating a voltage across the plate that's being picked up. But the circuitry inside this is set up so that when we cut off the magnetic field from that Hall effect plate, when we cut off the magnetic field by interfering with it, by putting ferrous material in between, the magnetic field making it to the Hall effect plate is less, and the voltage generated across the plate, which is proportional to the magnetic field, the strength of the magnetic field, decreases. And when the voltage decreases, the circuitry inside here is set up so that it does generate a digital signal output on the signal pin. So in short, what we have to do, we have to put a ferrous material between here, and it will send a digital output to the signal pin on this. So what we do is we send that signal pin in through port A. We could use any of port A4, port A3, port A4, or port A5. It doesn't matter. I'm using port A5 just because that's what I currently have the microcontroller programming to do. Before I tested the analog to digital converter, setting out all the inputs, or all of port A is digital, I first tried testing different pins and that didn't work. But right now I have this set up, so port A5 is what the signal of this Hall effect sensor will be sent to. So when we begin, that's pretty much it for how this circuit works. There's some other kind of trivial stuff, although it's somewhat important. Not too much though. Is obviously we're going to need a constant 5-volt source, and we're powering this from a 9-volt battery, so I have a 7805 voltage regulator, a bulk capacitor to filter, a capacitor across the power and ground, right up close to the microcontroller to filter any voltage spikes or noise or anything like that we have in the circuit. I'm using a 20 megahertz crystal with two 10 picofarad capacitors going to ground, so all just kind of unimportant but need to be there stuff. Well, it's kind of important, it depends on what part of this you're looking at, but I'll include the complete schematic on the web page, same spot as this video, electroburns.com, and that's pretty much it. But to show you more in depth what I mean by triggering this with a ferrous material, I will plug this in. I already went ahead and programmed this, but we're going to start from scratch, and I'll show you how to program this in the next video. but I am going to grab any material that I think will trigger this. I have a pair of pliers somewhere in here. Actually, I don't. Let's see if this will work. So, I have my set of calipers here, and if this material is ferrous, which I hope it is, otherwise this will be a pretty bad demonstration, and I block off the magnetic field there's a magnet in one of these two towers, from the Hall plate in the other tower, it should send a digital signal to the microcontroller, which will begin going through a sequence, not the sequence we're going to use to display an image in midair, but a sequence that I was just testing to see if it worked. So right now, I am... Alright, let me go find my pliers. And I'm going to zoom out. Alright. So, when I put the pliers between the two towers of the Hall effect sensor, you'll see the LEDs go on. And I'll try and keep my hand here and zoom in on the LEDs, because turning this on reminded me of one more thing that I wanted to talk to you about. I mentioned we're not going to deal with pulse width modulation, but you might be wondering why I have 8 different colors. I have not only red, green, blue, but I also have white, yellow, purple, turquoise, and black. Well, if I'm spinning the LEDs around and dealing with red first and then green and then blue, if I don't deal with pulse width modulation, there are 8 different colors I can get. Obviously red, where I have just the red LED on, the green and the blue LED off. Green, blue the same way. If I turn all 3 LEDs on in the same location when it's their respective turn to go around, I'll get white. If I turn red and green on, I'll get yellow. If I turn red and blue on, I'll get purple. If I turn green and blue on, I'll get turquoise. Or I could just leave the LED off. So, on this display, we'll be able to display 8 different colors. Red's on the far right, next is green, blue, white's in the middle, just to the left of it, yellow, then purple, turquoise, and black. So, I covered pretty much all the main points that I wanted to talk about in this tutorial. Again, I know I said this a few times, but at electroburns.com under, what is this, projects and persistence of vision display, under this particular tutorial, on the same page I am going to post a schematic, and I will take the time and painstakingly draw out every single LED for this tricolored LED array, I guess you could call it. And that's pretty much it, so thanks for watching, and I'll see you guys next time.